space dock, Captain. All ships ready for work.
Set course for Vulcan.
Aye, aye, Captain. Course laid in.
Maximum warp. Punch it.
During the last century, there has been an ongoing strive to fly higher and higher, sending a man into air, then into space, and finally into the moon. Man has always been trying to go further and further into space, as humanly possible, with upcoming missions going to Mars and possibly to the stars in the distant future. The imagination of spaceflight is never ending, but reality has its limits. There are physical boundaries which simply cannot be broken. In spaceflight, it would take tremendous amount of energy to get an object close to the speed of light. Even if it were possible, the nearest planetary system is 4.2 light years away from Earth. That is, maintaining the tremendous amount of energy to travel near the speed of light for more than 4 years to get to the next planetary system. This simply cannot be accomplished with an object the size of a spacecraft. Here is where the Mexican physicist Miguel Alcubierre sought out to find a new approach to find a way to travel through space, and hence created the first theorized warp drive.
In 1994, a Mexican physicist named Miguel Alcubierre was watching one of his favorite TV series, Star Trek, when Captain Kirk has to go to warp speed, and all of a sudden he thought, how could that be possible? Deriving from Einstein's field equation from general relativity, he proved that it is possible in theory. Even though the speed of light is really fast in comparison to the speeds that we have currently reached in the scale of the universe, this is relatively slow, so finding a new way to travel really far distances faster than light is indispensable to make interplanetary travel possible. This idea started in the mind of Alcubierre as he was trying to make his television series possible. But nowadays, the Alcubierre Warp Drive has reached a point that even NASA has a special team called Advanced Propulsion Physics Laboratory, better known as Civil Works Laboratory, that is currently working on experiments in order to try and prove that the Alcubierre Warp Drive is possible. When the theory was first published by Alcubierre, the scientific community only thought of the paper as something fun, because Alcubierre was only trying to prove that his TV show was something that could happen in real life. But it was estimated that the current mass of the observable universe will not suffice the energy requirements of the Alcubierre Warp Drive. However, it was later proposed that it could be possible with negative energy densities, but we, on the other side, have never seen negative pressures except in quantum scales, as with the Casimir effect. Another way of making it possible is having exotic matter with a negative mass, but this is not currently proved, so the Alcubierre Warp Drive is on standby.
The proposed method for the change of geometry of space that could cause a change in the fabric of space ahead of a spacecraft, so the geometry of space contracts in front of it and expands behind it. So the ship will ride the wave inside the region of the flat unaffected space, known as warp bubble. So you will be carried along the region due to the drive. But you will need a configurable energy density field lower than the energy density of vacuum. This is called negative energy or negative mass, and this idea is based on a solution of the Einstein field equations in general relativity, and the energy density equation is given by this. The fact that this expression is everywhere negative implies that the weak and dominant energy conditions are violated. In a similar way, one can show that the strong energy condition is also violated. The Casimir effect is the perfect example where you can generate negative energy by joining two plates with a sonificator and amplifying the effect.
EU's Laboratories is one of the laboratories previously mentioned that were created to work on Alcubierre's drive theory in NASA. This laboratory has created the shape of the spacecraft that reduces the amount of energy needed and has also been optimized to the shape of the warp bubble. This is an impactful finding since the shape of the spacecraft itself, alongside with the warp bubble, has the front end being pulled to the destination and the rear end being propelled from the origin.
The geometry of spacetime is given in a three-dimensional coordinate system. Given the following equation, the metric of spacetime can be written as assuming the spaceship moves along the x-axis, we want to find the metric that pushes the spaceship along a specific trajectory described by a function of time xt, and the metric is given by and the final equation is that. Where the velocity is given by and the vector r is and where the f is the function that represents in these equations we imply that g equals c equals 1, and in which alpha equals 1, as we established, and alpha gives the interval of proper time between nearby hypersurface and as measured by observers, and the vector bi, these two vectors, relates the spatial coordinate system on different hypersurfaces. And the gamma, that was gamma I equals delta ij, represents the trigonometric of the hypersurface equaling a Kronecker delta, and this only represents the velocity, the change in position over time.
A few moments later.
These r and rs, we can establish that with r bigger than 0 and sigma that is also bigger than 0, tending to infinity. If this sigma tends to infinity or large values, the function f of rs could be the limit sigma tending to infinity of rs that equals 0, and it equals 1 for rs in the space of r to r, and 0 for otherwise. So that's the meaning of sigma, these values. And with all the above definitions, the metric that can be rewritten as squared, that this equals also the same value dt tau squared, and this can be rewritten dt squared minus dt squared plus partial x minus ds, that is the velocity, times f of rs dt, and this is the value of ds.
Since we have a three-dimensional hypersurface that is flat, the curvature of spacetime can be expressed by an extrinsic curvature tensor, k subindex ij, and the tensor gives us information about a third-dimensional hypersurface inside a fourth-dimensional spacetime. This can be written as k subindex ij equals 1 over 2 alpha times d subindex I beta subindex j plus d subindex j beta subindex I minus a partial of g I j over a partial of time. This can later be rewritten as the d subindex I represents a covariant with respect to gamma subindex ij that we mentioned in the beginning. and can be rewritten as and these changed as a partial. The expansion of theta is of the volume of the components of spacetime that can be written as and not so obvious, but this can be easily rewritten as and this right here is the York time equation. And this is a measure of the contraction and expansion of space with this equation.
To define the time equation, we use general and special relativity. We have to use an example to illustrate this. Let's say we have a star A and we want to reach a star B. We have a spacecraft. In order to don't violate the space in star A, we're going to start at distance b from the surface. Now, the initial acceleration is 0, and we have to increase it to a constant value of a. In that time, until we reach the middle, we're going to have the same acceleration. And from the middle to the star B, we're going to use the same but negative acceleration in order to reach point B apart from star B. Using this example, we can use and define the time equations, which are defined by this. Since the distance between the star and the starting point is irrelevant to the giant distance between each one, we can redefine this equation in a more simplified one by using approximations. Being this equation, the time we use to travel between one point and the other using the Alcubierre Warp Drive. Just imagine space travel. Space travel is one of the most seeked topics, and if ever shipped, the applications could be infinite. Alcubierre's Warp Drive shows a possibility to explore space, exoplanets, black holes, star clusters, well, all the wonders of the universe. Being able to observe with more precision this type of phenomenon will grant scientists enormous search material in order to understand the universe we live on. Nowadays, resources are scarce, and the research projects are in need of them. With the warp drive, inorganic materials could be harvested from other celestial bodies. With that way, we could improve the quantity and quality of these projects. Well, just imagine space travel.